Hello, everyone who may be watching. This is a project that I did for my junior level instrumental chemistry course, and it follows determining some analytes in a diet soda beverage by capillary electrophoresis and HPLC methods. If you're an employer or evaluating me for grad school, I really hope that you find this awesome. Would love, maybe you're doing a little background check or something. Hopefully you'll find this to be cool. Otherwise, this is just to get an idea of the kind of pacing that I'm going to have when I determine, when I give this presentation in front of my instrumental class. So what was the goal? Well, the goal was very simple. It's just to determine three analytes of interest: caffeine, aspartame, and benzoic acid. We'll get into what those are. Using HPLC and capillary electrophoresis, two chromatographic methods. Remember, CE, you're going to use buffer reservoirs, apply a voltage across a capillary. It's going to migrate based on its electrophoretic mobility and its electroosmotic flow, and you're going to separate things that way. But also, don't forget the HPLC. It's like a column that you did in organic chemistry, just beefed up, add some pressure to it, and you're going to get some nice peak data from that. So two very nice analytical methods. So let's get into how we use that. But actually, before that, we're going to talk about what each analyte actually is, because why would we be wanting to detect something that we don't care about? Well, caffeine, of course, caffeine equals happiness, right? It's in a lot of your drinks. It causes an upping effect, and it is primarily stemmed from this idea that caffeine is blocking adenosine receptors, and that's what's going to make you feel more awake, more alert, and the other side effects. Okay, what is aspartame? Well, aspartame is a dipeptide, aspartic acid, and phenylalanine. And when we put this on our tongue, it's going to mess around with some receptors, and we're going to see that it's 200 times sweeter than sugar, so a very potent sweetener. But notice it's completely protein-based. It's not at all carbohydrate-based, so this is good for diabetics who want to overcome the challenges of a very carbonous world, so to speak. Okay, and benzoic acid or benzoate, right? We know that we're going to be talking about sodium benzoate here because that's how it's used, but benzoic acid is the acidic form. Sorry, I don't know why that took me so long. But when we found that when we put sodium benzoate in our food, it has antimicrobial properties, and it extends shelf life of about 6 to 12 months. But the FDA does not allow in beverages to be over 1,000 ppm. So very, very, very liberal on this idea. More liberal. They're freeing of this idea of using benzoate because it's relatively safe in low doses. And we'll see in our in my research here that we indeed do find it to be under safe limits. And maybe if you took organic chemistry, you worked a lot with benzoic acid or benzoate, that system in general. It's a very common organic acid because it's just so simple, and it has the characteristic structure of these needly-like kind of compounds. So I'm sure you've seen it in your organic chemistry ventures. Okay, so the methods. HPLC and C are going to provide the same thing. They're going to tell me the concentrations of all three analytes. Then I'm going to do a student tease test and across the two methods and see, well, do they agree? And then in their own division, right, to see that's going to tell me reproducibility among the two methods. The way I'm going to get precision and accuracy is I'm going to see, okay, do the values that I got from both methods compare with known values? So the two sort of statistical tests, which will give me a very clear idea of, one, are the two methods comparable, and two, do they agree with what the rest of the world says? Okay, so let's start with the HPLC method. I pulled this from a Indonesian journal. Very, very nice paper here. They had a very nice method. Everything was written out so well. It was actually an optimization method, but the way that they presented it was absolutely amazing. And they messed around with pHs and all this stuff, temperatures, mobile phase compositions, And what they found is the best conditions, C18 column, 40 degrees Celsius column temperature, 80-20 phosphate buffer at 3.8 pH, and methanol as your mobile phase, and then a flow rate of 0.55 mils a minute. So kind of a lot there, but a 10-minute acquisition time, so per sample, that's actually pretty good. And then you do a photodiode array detection at 200 nanometers. So a little odd. Typically in simultaneous detection, you want to do 215, but here they say 200. And then a 10 microliter injection volume. And for sample prep, all you have to do is degas it for 2 days. We'll get to a different method that I found a little later. They do sonicate it, but at the time that I was developing this method, we were just going to allow them to degas by open beaker. I didn't know we had a sonicator basically, because someone was being a little dumb. But that's okay. You take 5 milliliters of sample, you dilute it in 50 milliliters of your mobile phase, and then we're going to take 2 mils of that solution fully mixed and dilute it to 10 milliliters, and then we're going to put it through a Buchner filtration, so vacuum filtration basically. So that was basically the whole method, but I didn't get any results, and the reason is because the HPLC broke on me. Now, I think the reason for this is that when I made my phosphate buffer, I made it way too concentrated. Now, typically your run buffers need to be around 20 millimolar to, I don't know, maybe 100. I think mine was bordering on 100. So what I think happened is I clogged the machine, because when you put all that under pressure, you might get some dissolution and then it clogs the column. So that could have been an issue. But yeah, I felt like throwing the HPLC out the window, right? I was not getting good data at first in the CE method. I just wanted something different. And then the HPLC decided, nope, I don't care. I'm not going to work. So maybe my fault, maybe the machine's fault. Shimatsu will figure it out, and blame me if you want. Okay, CE method, right? The capillary electrophoresis method. This paper came out in 1997. Very old paper by Walker's group, and it looks like he might even have a brother, Edward. So pretty cool. It's just a short communication paper. Just to communicate to the rest of the scientific community, well, if you're looking to do beverages, do this. And it found me, so thank you. Thank you to the Walker brothers. I'm going to assume they're brothers. And then this Spencer guy, too. So very nice. And they come from Weber State University in Utah. Okay, so the conditions that they call for is very rigorous. Now, they say that for every sample, you have to do a 15-minute sodium hydroxide wash, a 15-minute 0.1 molar NaOH wash, a 15-minute water rinse, a 5-min glycine buffer wash, and then you inject your sample, and then it's 20 kilovolt separation. It is a very tedious and, quite frankly, inefficient from maybe in an analytical standpoint it's good, but in an industry application, this is just not great. And it was a 5-minute collection period that they said on the paper, but I bumped it up to 7 just so I can see the full picture. I let it run overnight, so it was no biggie of a time constraint. But yeah. Okay, sample prep. So I made 2 sets of solutions. We'll get into why I made this decision. It actually I made the first 1-fold dilution of samples first, and then I found that they were terrible. So then I made a 6-fold dilution, and that seemed to fix things. And the first time around with the 1-fold dilution, I degassed them in an open beaker, and this was kind of a problem, as we'll see in a little bit. But we're going to see some band overlap, a lot of degradation, because it's in an open container in sun fluxing conditions, so not great. So I actually did find a sonicator, despite someone telling me that there wasn't a sonicator, which was really nice. And I was able to then, in my next set of trials with samples, I did the 6-fold dilution. I degassed them by sonication, and the results we'll see came out a lot better. So I'm going to go through both, but I just wanted to make you aware, because this can be a big point of confusion if you don't get it. Okay, standards. I made a set of standards caffeine, aspartame, benzoate in DI water. I also made a set of standards in glycine. The paper had a fundamental flaw of not telling me how the standards were produced. So I kind of overlooked this fact when I was preparing. I was like, oh, I'll just put it in water. Well, if you apply a voltage across pure water, it's not the same as your glycine buffers. So it can get a little confused and you get weird data. That's why I decided to make the caffeine and aspartame in glycine instead. It was just a lot easier. Or it gave me better data, I should say. Okay, so let's go through some of the results of the standards. You can see that at about 3.7 retention time to up to 4, we're getting some sort of peak for a sodium benzoate, peak. But notice the signal, you lose a lot of your signal to noise as you go from times 10 to the second and then times 10 to the 1, right? You're really dropping the signal to noise. It just melds into the baseline. And also the retention time gets completely destroyed. So anywho, let's continue. I got a really good R² value among all three. So I'll take it. Not great. It's not. I'm not gonna lie. The benzoate standards weren't the best, but for what data I got, I'll take it. It's good. We'll see later. Caffeine standards, very simple, although they gave interesting data. I only got 3 for the samples in DI water. This is going to be a common problem when we did the standards in DI water. The caffeine just melted right into the baseline, so integration was very tricky here. We had to integrate. The 200 was fine, the 20 was okay, and then the 2 was complete nonsense, and then below that, because I ran I think a 1 ppm, there was no peak. So tricky stuff here, can't lie. Okay, so the caffeine standard result gave a decent calibration curve. I practically threw this out the window, but we'll get to that in a little later. And then aspartame, very similar stuff. I'm not going to die on this hill. Retention times, however, for all of the different standards were, very, very good, very distinct. 3.5, 3, and 2.5. So I got about half a minute of wiggle room between the peaks. Okay, so this is the calibration curve I generated. It wasn't great. And none of the DI water standards were great, but I did use them in my first analysis, which we'll see. Okay, so now for the caffeine standards in glycine, I feel like these were a lot more coherent because I matched the phase of the run buffer. And when I did this, I could get up to the 20 ppm before I started to meld into the baseline. And you're going to see that I was able to, well, except for the 0.2 ppm standard where I didn't get any, I got too much noise. I was able to capture 200 ppm, 100 ppm, 20 ppm, and 2 ppm. So very good, not bad. And it gave me a decent R², more realistic, right? The last one was a little bit, when it was in pure water, it wasn't great. When it was in this, it was a lot better. Okay, aspartame, looking at that now, really great peaks here. I thought they were pretty good. And when we look at the data, we're going to see that we get a more realistic R² value of 0.9883. So not bad amongst 3 standards, three points. Not the worst. And we'll see that the error agrees with this. Okay, so let's look at the one-fold dilution trials of our samples. Okay, so I did Diet Coke, Diet Pepsi, and Diet Dr. Pepper. Diet Coke shares a similar theme with the rest of them in the one-fold dilution category, where we get this huge caffeine tailing. At 2.5, roughly, the caffeine peak begins to elute, and the peak is so broad it shifts the baseline for the rest of the chromatograph. So very bad stuff. We don't really want to see that. And to a significant degree, we go from, I think the y-axis there is in voltage. So the voltage is jumping like 5 kilovolt. I think that's what it's measuring. Something like that. Anywho, the point is that these peaks are not well resolved. They're not great, and in fact, that's what we see for the rest of them. Large tailing, not a great base separation. Although benzoate came out great. Benzoate gave amazing resolution from the baseline and other peaks. Dr. Pepper, similar thing. We won't get down on this hill too much. I just want to show you the different kinds of peaks I got. Okay, so when we compare these with our calibration curves, this is what we get. The advertised caffeine content is in red, and you can see that the caffeine content is pretty significantly off here. I mean, the blue bar is the DI standards, and actually for caffeine, it came out not bad. It agreed pretty well. But for glycine, which matches the samples better, right, and the standards, or sorry, just the samples, they match it better, and you're seeing, like for the example in Diet Coke all the way to the left, that calculated caffeine content has an incredible amount of error in it. And in fact, you see the same trend in aspartame as well, right? Diet Pepsi maybe got really close to it, but then when we looked at the glycine standards, which are better standards in general, right? It's just way off. Okay, so let's look at the percent error just to prove my point. In the DI H2O standards, caffeine was relatively well captured. I think this was by chance. But the percent error of aspartame got as high as 36%, so very not good for analytical chemistry. And the glycine standards, you can really see the error begin to come out here when we start to match to the samples themselves, right? The samples were diluted in glycine. We match it with glycine standards, and it's all messed up. So hopefully you can see how bad the idea of one-fold dilution is and DI standards are. And that's in fact why I decided to do six-fold standards. But some other niche sources of errors: aspartame dissociation. A peak at about 4.0 retention time is a phenylalanine peak, and phenylalanine is one of the residues on the aspartame dipeptide. And when it dissociates, it has this very nice, sharp, characteristic peak. It's chromophoric, so when it goes to the PDA detection, it's going to be absorbing quite a bit. So how could you fix this? Well, maybe sonicate the samples instead. And this is, in fact, a change I made. Well, I wanted to sonicate originally, but again, someone told me that there wasn't a sonication tool, and, well, I just had to degas it in air. So sonication would have helped here. And I think that's why, if we go back to aspartame, it was so wildly off because of that dissociation. Maybe in the case of the DI standards. Okay, another one is band broadening. We already talked about this. That caffeine peak is too big. Dilute the samples more. So those are the changes I made. That's why I picked to do six-fold dilution with sonication. So let's get into how those came out. So with six-fold dilution, the peaks came out a little funky, but I was able to integrate them decently well. But they came out a lot more coherent. Look at the caffeine peak here. Sure, the tailing's bad, but you can see that the slope here in Coke Trial 1, for example, really begins to mellow out, whereas earlier we saw complete overlapping into the aspartame peak. So it gave better resolution for aspartame, which is what we're going to see as a really, really, really important detail. So Coke came out okay. Pepsi came out really good, although this was a kind of a pain to get to integrate right. And Dr. Pepper came out exceptionally well. Okay, so what results did I get now? Well, if we look at the caffeine content, all but Diet Pepsi gave a really, really good result, less than 15% error. Diet Pepsi, will get into why I think I didn't get quite a good result here, but the caffeine content, I did pretty good on, I'd say. And same with aspartame. The levels agree with the glycine standards when I compared them. They compared really well to the known values, and that's really, really satisfying to see. And I avoided talking about sodium benzoate. You were probably like, well, where did that go? It's here. I wanted to save it for the end. With the one-fold dilution and the six-fold dilution, they agree phenomenally, which is great. So those peaks agreeing so well tells me that it's reproducible for benzoate. Probably the best, most accurate thing I got from this project here. And it's all about 5 times less than the FDA limit, so that's good, right? We're not killing ourselves with benzoate. So percent error, let's talk about it. Did we go over the 1,000 benzoate limit? No, we did not. Percent error on caffeine, well, among Diet Coke and Diet Dr. Pepper, we have 9.24% and 5.61%. Very good. It's not great. The method needs to be refined more and to a higher degree before you can even implement this, right? You want to get that percent error down maybe less than 1%. Or, you know, there's other things we'll talk about. But Diet Pepsi, right, decided, I don't care. I'm going to give you 46.2% error. Whatever, I don't care. You're a sucky beverage anyways. Percent error on aspartame, though, look at that data. That is great. That is, well, not great, but I'm satisfied with it. 15% error, I'll take it, whatever. It could have been like 30%, you know. So it's decent data. It's decent. You know, I spent a whole how long on this. I'll shove smoke up my ass if I feel like it. Okay, so what is the source of error causing the error here? Well, I believe that the reason that this data came out with a decently high error is because of poor sampling. Now, when I sampled initially with the 1 full dilution, I amalgamated like 3 cans of each soda into one big solution so I could get a good homogenized kind of sample from what I was given. However, in the second go around in the 6 full dilution with sonication, I just didn't have time to do this. So what I had to end up doing is what I had to end up doing was just pulling. Oh, I'm brain farting. 1 second, guys. Let me lock in. Let me lock in. Okay, so I did poor sampling here. I only did 1 can of soda, which, if we think about it, in the case of Diet Pepsi, for example, what if that Diet Pepsi can came from the factory and maybe the machine did a big oopsies and didn't put in the right amount of caffeine in it, right? And that can be said for the Diet Coke. There's going to be small deviations in manufacturing of these beverages, right? So what I would want to be doing next, right, if I wanted to further this work, I would take many, many, many samples. I'd go around many, many types of stores if the budget was allowed and pick out different types of these sodas, right, in cans, of course, because that's what we're looking at specifically. So look at these canned beverages and get a good representative sample of the population, right? In the case of my project, I just didn't have that, right? And I think that's a fundamental flaw that we all will suffer with in our presentations here. So thanks for listening. That's all I really have to say. Sorry about that brain fart at the end. I don't know what happened. My brain does that. I'm a bad speaker sometimes. But I hope you guys enjoyed, and that was my project. So take care.